numbers, dates, and quantities in operations. This lesson explores how to work with numbers, dates, and quantities in real supply chain and operations datasets. These concepts affect everything from inventory tracking to sales forecasting. You will learn how to load, inspect, and analyze datasets containing operational numbers and timestamps. We will solve real problems in procurement, sales, supply, and fulfillment. You will build core skills for recognizing business patterns in the data. Running the cell now. We start by importing the libraries needed for working with supply chain datasets. We import pandas for tabular data analysis. We import OpenML for accessing real open supply chain datasets. We import the warnings library. We silence warnings so our analysis is not cluttered with warning messages. Running the cell now. Understanding operational data. Supply chain and operations data tracks flows of goods, orders, demand, suppliers, and fulfillment. Data is usually organized as tables with columns for dates, numbers, and identifiers. Common fields include order dates, delivery dates, quantities, stock levels, and purchase values. Mistakes happen if you confuse date formats, misinterpret numbers, or forget that operations data can be messy and incomplete. Handling missing values and checking for inconsistencies are part of every analysis. Running the cell now. Let us load a real e-commerce order dataset and inspect the purchase and delivery dates. We load the OList order fulfillment dataset from a public URL. We convert purchase timestamps to date-time objects. We also convert delivery timestamps to date-time. Here is how the purchase and delivery dates look for the first 3 orders. Running the cell now. This output shows the first 3 orders with their purchase and delivery timestamps correctly parsed as dates, illustrating how operational data records key events over time. Notice the clear date format and time difference between purchase and delivery, which is critical for analyzing fulfillment speed and detecting delays. Properly converting these columns to date time ensures accurate time-based calculations in later analyses. Try exploring which date columns exist in the dataset. A typical operational question is, how long does it take to deliver an order? We calculate the number of days between the purchase and delivery date for each order. This new column helps us spot outliers and analyze delivery performance. Let us look at the delivery times for a few sample orders. Running the cell now. This output shows the first 3 orders with their calculated delivery times in days, highlighting how long it took from purchase to customer delivery. Notice the delivery_days column is numeric and reflects the time difference, which is crucial for analyzing supply chain efficiency. This step connects date fields to meaningful operational metrics, reinforcing the importance of correct date handling in messy, real-world data. Practice: what is the shortest delivery duration in this dataset? Missing date values are common in operations. Let us check for missing delivery dates. We count how many orders are missing a delivery date. This tells us whether our dataset is complete or if we need special handling. Running the cell now. This output shows that there are 2,965 missing values in the delivery date column, highlighting potential gaps in the fulfillment data. Noticing these missing dates is crucial because it affects how we track order completion and delivery performance. This reinforces the lesson point that operations data can be incomplete or messy, requiring careful handling before analysis. What could cause a delivery date to be missing? Think about cancelled or pending orders. Let us look at a real inventory operations dataset from OpenML. We download the manufacturing and inventory operations dataset from OpenML. We retrieve it as a pandas data frame. If there is a target column, we combine it with the features. We print the number of records and columns. We preview the first 3 inventory entries. Running the cell now. This output shows the inventory operations dataset with 32,769 rows and 10 columns, illustrating the typical scale and structure of operational data. Notice the columns mainly contain identifiers rather than human-readable labels, highlighting the importance of decoding and understanding coded fields in supply chain data. This step is crucial to properly interpret the flows and roles tracked before further analysis. Notice how the dataset structure differs from the order data. We often need to sum inventory quantities to understand stock levels. We check if there is a column called quantity in the dataset. If it exists, we sum it to see the total stock available. We display the total inventory across all items. If there is no such column, we print a message. Running the cell now. This output indicates the quantity column is missing from the inventory data, highlighting a common issue in operational datasets where expected fields may be absent or named differently. It's important to verify the presence of key columns like quantity before performing aggregations, as relying on incomplete data can lead to errors or incorrect insights. This check helps ensure the data aligns with operational metrics like stock levels before analysis. Try to find other quantity or count columns in this dataset. Now let us inspect a supplier performance procurement dataset. We load the supplier performance dataset from OpenML. If there is an invoice date column, we convert it to date time for analysis. We preview a few rows to check what date and numeric columns are available. Running the cell now. This output shows the first few rows of a supplier dataset after loading and attempting to parse the invoice date column. Notice the table includes employee and payroll details rather than typical supplier or order data, which highlights a key lesson: datasets may contain unexpected or inconsistent fields. This reinforces the importance of inspecting data carefully to correctly interpret operational records and avoid mistakes with date and numeric columns. Explore, list the date columns you see in this supplier data. Late deliveries can cause many operational headaches. Let us check if the supplier ever misses deadlines. If both actual and expected delivery dates exist, we convert them to date time. We calculate the difference to see how late or early each delivery was. We display several rows of these metrics to look for possible late shipments. If those columns are not present, we note it. Running the cell now. This output tells us that the dataset we are working with does not have the expected delivery date columns, which means we can't analyze delivery delays yet. This highlights a key point in operational data: always verify that crucial fields like dates are present before performing calculations. Missing or inconsistent columns can halt your analysis, so it's important to confirm data completeness early. Would this kind of delay calculation be useful for your organization? Let us see how many orders are placed per day in the OLIS dataset. We group all orders based on the purchase date, ignoring time. We count how many orders occurred on each date. We print the result to get a feel for daily activity. Running the cell now. This output shows the number of orders placed on each purchase date, aggregated from the dataset. Notice how the dates serve as the index, with the count of orders as the value, highlighting that early in the dataset, there was typically just one order per day. This helps us understand the daily order volume and reinforces the importance of correctly handling date columns when analyzing operational data. Try plotting the distribution of daily order counts. Sales forecasting often depends on historical numbers, promotions, and calendar effects. We load a real sales forecasting dataset from OpenML. We combine all features and the target variable in one data frame. We preview the first 3 rows to look for numbers and dates related to operational flow. Running the cell now. This output shows the first 3 rows of a sales forecasting dataset with 78 columns of operational features like NCD, AI, and NAD, which likely represent different product or customer attributes over time. Notice the numeric nature and the wide shape, highlighting the complexity and multidimensionality of supply chain data. This preview helps us understand the structure before exploring key dates or quantities, reinforcing the importance of carefully interpreting operational data columns. How many rows and columns are in this dataset? Use sales_df.shape. It is important to know which columns refer to time or calendar information. We list all columns that seem to contain date or time values. If a date column exists, we convert it to date time for further analysis. This allows us to align operations over time and understand daily or weekly cycles. Running the cell now. This output shows that no columns containing date or time were found in the sales data, indicating a potential issue since operational datasets usually include such fields. The code's intent is to identify and convert date columns for accurate analysis, so an empty list means you might need to check the data source or column naming for date-related information. This highlights the importance of verifying your data before proceeding with time-based operations. Dates are crucial for understanding how operations unfold over time. Visualizing numbers helps us spot outliers and business trends. We import matplotlib for plotting. We select numeric columns from the sales dataset. If numeric columns exist, we display a histogram. We set descriptive axis labels to help interpret the chart. We display the plot showing the frequency of values. If no numeric columns are present, we note this. Running the cell now. This histogram shows the distribution of the first numeric column in the sales data, likely representing quantities like order amounts or sales values. Notice the spread and frequency of values, which helps identify common order sizes and potential outliers. This visualization connects to the lesson by highlighting how numeric operational data can reveal patterns and inform business decisions. Notice how some values might cluster at certain points. What could this mean for supply chain planning? Business teams often want to smooth daily metrics to spot trends. Let us calculate a 7-day rolling average delivery time. We sort the OLIS dataset by order date and remove entries with missing delivery days. We use a 7-day moving window to calculate the average delivery duration. We print the actual and smooth delivery times for sample days. Running the cell now. Here, we see the daily delivery duration sorted by purchase date with a 7-day rolling average calculated to smooth out short-term fluctuations. Notice that the rolling average starts showing values only after the first 7 data points, highlighting how this method captures ongoing trends rather than isolated days. This helps reveal broader patterns in delivery performance, a key insight when managing operational timelines. This pattern is used in forecasting and service-level reporting. Older data can be grouped by month for high-level operational analysis. We add a column for the month of each order. We count how many orders were placed in each month. This helps managers see big-picture business trends. Running the cell now. This output shows the count of orders placed each month, derived by extracting the month from the full order timestamps and grouping orders accordingly. Notice how the volume ramps up over time, reflecting growing demand or data coverage, but also that some months have very few orders, which could indicate incomplete records or seasonal patterns. This highlights the importance of correctly handling date fields to accurately track order flows in operational data. Try grouping by week and comparing the result. Operations teams need to understand seasonality to avoid stockouts. We extract the ISO week number for each order. We group by week and count the number of orders in each season. This shows how customer behavior changes over the year. Running the cell now. This output shows the count of orders placed in the first 5 weeks of the year, revealing early season weekly order volumes. Notice how the order counts generally increase from week 1 to week 5, indicating a potential seasonal trend in demand. This helps illustrate how operational data can track patterns over time, emphasizing the importance of correctly extracting and grouping by date fields for accurate analysis. What kinds of sales spikes would you expect in certain weeks? Can you spot any peaks? A common key performance indicator is the share of orders delivered within a certain number of days. We set an on-time threshold. Let us say an order should arrive in 5 days or less. We count the number of delivered orders. We count the number delivered on or before the threshold. We calculate and print the on-time percentage. This KPI helps diagnose supply chain speed problems. Running the cell now. This output shows that only about 20% of deliveries were made within 5 days, highlighting a key operational metric, on-time delivery rate. Notice how the code calculates this by counting deliveries with known delivery times and those meeting the threshold, reinforcing the importance of correctly handling missing or incomplete data in operations analysis. This insight helps identify potential delays or inefficiencies in the supply chain. Try changing the threshold to see how your KPI changes. Missing or corrupt data must be handled for reliable operations metrics. We check how many delivery days are missing. If any are missing, we print a warning and fill with -1 to flag them. We copy the data frame to avoid overwriting raw data. If none are missing, we print a positive message. Running the cell now. This output highlights that 2,965 orders in the dataset lack delivery day information, signaling missing or incomplete operational data. The code handles this by identifying these gaps and replacing the missing values with a placeholder, -1, which helps prevent errors in later analysis while preserving the data structure. This step is crucial for accurately managing and interpreting supply chain timelines in messy, real-world data. YouTube, search for supply chain data cleaning for more tips. How else could you handle missing delivery times? Errors can result from misentered data, like deliveries before their orders. We filter for orders where the delivery date is earlier than the purchase date. We print how many suspicious records we found. If we find any, we list some of the problematic records. Running the cell now. This output shows there are 0 cases where delivery dates occur before purchase dates, which is good. Such a scenario would indicate data errors. The code checks for these impossible date sequences to ensure the operational data's integrity before further analysis. Noticing 0 invalid entries confirms the date columns are consistent and reliable for understanding order fulfillment timelines. Check, filter for any other impossible date errors you can imagine. Incorrect merges can quietly damage your supply chain analytics. Let us simulate a faulty join. We take a slice of order IDs and purchase dates. We take a non-overlapping slice of order IDs and delivery dates. We merge on order_ID using an outer join, showing which records match or miss. We print the result and see where matches fail or duplicate. Running the cell now. This merge output highlights how misaligned subsets can cause missing matches, with many rows marked as left_only or right_only, indicating dropped or unmatched orders. Notice the NAT, missing dates, in the timestamps where data exists only on one side, underscoring the importance of consistent IDs and properly aligned data when joining operational tables. This demonstrates a common pitfall in supply chain data analysis. Incorrect merges can lead to incomplete or misleading views of order timelines. Practice: what would change if you used an inner join instead? Aggregating orders or inventory by item is core to supply chain planning. If the OLIS data has product IDs, group and count orders per product. We sort and display the most ordered products. If not, we note the absence. Running the cell now. This output shows that the dataset does not contain a product_ID column, so the code cannot aggregate orders by product. This highlights an important lesson: operational data can vary in structure, and it's crucial to check that key fields exist before running analysis to avoid errors or misleading results. Always verify your data columns to ensure your code aligns with the dataset's contents. Try other aggregation levels such as supplier or region. Visualization helps operations teams monitor trends over time. Let us plot a rolling on-time delivery KPI. We pick a 7-day on-time threshold. Sort by order date for rolling calculations. Create an on_time flag for each order. Calculate a rolling % KPI over the last 30 orders. Plot the KPI trend over time. Set chart titles and axis labels for operations review. Display the rolling on-time performance. Running the cell now. This plot shows the 30-order rolling percentage of on-time deliveries, where on-time means delivered within 7 days. Notice how the trend smooths short-term fluctuations by averaging recent orders, helping us track delivery performance over time. This visualization highlights the importance of consistent date-based metrics in operational data to monitor and improve supply chain efficiency. YouTube, for more on operational KPIs, see channels like Analytics Video Supply Chain. For weekly reporting, group key quantities by ISO week. We use the week column to sum up the number of orders in each week. We print a few weekly counts for operations reporting. Running the cell now. This output shows the total number of orders placed each week, capturing the order volume trend over time. Notice how the counts increase from week 1 to week 5, reflecting growing activity or demand. Summarizing order counts by week helps us track operational patterns and identify busy periods in the supply chain data. Which week has the highest order count? Try finding the maximum. Let us combine what you have learned. Find the week with the shortest average delivery time. We consider only positive delivery days. We group by week and compute the average delivery time per week. We identify which week had the fastest mean deliveries. We print this key operational insight. Running the cell now. This output highlights the week with the quickest deliveries by calculating the average delivery days per week and finding the minimum. Notice how filtering for positive delivery days avoids skewing the average with invalid or missing data, reflecting the importance of data cleaning in operations. This step connects to understanding how delivery speed fluctuates over time, a key insight for monitoring supply chain efficiency. Operations teams use this kind of analysis to identify best practices and repeat peak performance.